All right, ladies and gentlemen, in this video, we are going to be diving on into my absolute favorite topic when it comes to geometry, and specifically within our logic and reasoning unit, and that is mathematical proofs. Yes, proving statements to be true. So in this video, we are going to first and foremost define what a proof is, define what a theorem is, and we're going to complete a couple of proofs, not from scratch. We're going to look at these kind of almost as a drag and drop or a fill in the blank to start some things off with. But the reason why I love these so much, guys, and it's kind of all based on in the definition. So a proof just simply is a logical argument that uses deductive reasoning to show that a statement is true. So now we've already talked about deductive reasoning. Deductive, remember, is all about utilizing facts and evidence to support an argument. Facts and evidence to support an argument. And so when we think about these proofs, guys, there's so many connections to the real world, whether you're in law or whether you're just literally trying to prove to your parents why you deserve to go to the mall this weekend or to go out to the movies on a Friday night. Like everything we do and all the decisions that we make when we're trying to sell ourselves or sell a product to someone, there's evidence behind why what we are saying is true. And so that's why I just absolutely love this section as we get into proofs. We're going to be having proofs through the entire school year. And so this is just the very, very basics and the starting of it. For the most part, we're going to be looking into what is called a two-column proof. A two-column proof is just kind of numbered statements on the left and then your corresponding reasons on the right-hand side. And so let's take a look. So in this example, what you see in this very first proof, and this is what we'll have in all proofs, is a given and a prove statement. You are given some information, and your goal is to take what is given and make a logical argument and prove what the prove statement actually is. And so in this example, what we see here, this is a two-column proof. Now, I have given us most of the information in this example here. But what I want to go ahead and do is I want to kind of just start the proof off as not a blank slate, because I think we do need a little practice just identifying what some of the key things are first and foremost. So what we're going to learn is that we start every single proof with what is given, just like it was for our algebraic reasoning. We start every single proof with what is given. So in this diagram, we know that angle 1 is equal to angle 3. So from that information, we have to deduce all the way down to realize that the measure of angle EBA is equal to the measure of angle CBD. All right, well, we already got one thing given to us, that by the angle addition postulate, angle 1 right here, is equal to angle 2 right here, and plus angle 3 right in here is equal to the big angle of EBA. Remember, our angle addition postulate just says that two smaller angles make up a bigger comprised angle right in here. And now where I was talking about with angle 1. Angle 1 right here makes on up. Now, be careful. It's not another angle addition postulate. Notice what we know from the beginning. We know that 1 equals 3. So that means at any time I can swap out, interchange, or substitute 1 and 3 because they're equal to one another. And so that helps us because we're trying to introduce angle CBD. We'll take a look here. Angle CBD is 1 plus 2. So now we're getting somewhere. So now angle EBA equals 2 plus 1 because I swapped out angle 1 and angle 3. So then as we continue to go on forward, it looks like we're going to use the commutative property of addition. Well, the commutative property of addition just means that we're going to change the order of our values that are being added together. So we're going to go ahead and make that measure of angle 1 plus the measure of angle 2. And then once again here, we see that the next thing being statement, the next statement we are making is using the angle addition postulate. Well, what does 1 plus 2 equal? Well, 1 plus angle 2 equals angle CBD. And there actually should be a measure of CBD here, so measure of angle CBD. Well, now look what happens. You have two different angles, EBA and CBD, but they both equal the measure of 1 plus the measure of 2. Well, if they both equal the same thing, this is exactly what our transitive property of equality tells us. If A equals B and B equals C, then A equals C as well. And that is our transitive property of equality. So that's our very first proof. Let's take a look at another one together, where it's more of a kind of a fill in the blank. In this example, we're going to be utilizing some segments. So once again, what is given to us always starts. So T is the midpoint of SU, and the goal is to get to show that X equals 5. So we start with what's given. T is the midpoint of SU. The fact that T is the midpoint tells us that ST and TU are congruent to each other. So they are congruent because T was the midpoint. So you ask yourself, what physically tells you that ST and TU are congruent? The definition of a midpoint. Well, then it's going down here and it says ST is equal to TU. So we go from congruent to equal. Well, why did we drop the congruency in the first place? Because we want to finish in equal signs. So we want to get rid of the congruency and start introducing equal signs. And so when we think about congruency and equal, when two segments are congruent, they physically are equal in value or in length. And so that's the definition of congruent segments. So then we go ahead and say that ST equals TU. The next statement we are making is that 7x equals 3x plus 20. Well, let's go back on up here. ST physically equals 7x. TU physically equals 3x plus 20. So what did we do? We substituted 7x for ST and 3x plus 20 for TU. The next thing says that we're using the subtraction property of equality. So whatever I do on the left-hand side had to have used the subtraction property of equality. Well, what would you subtract? So we are physically subtracting that 3x from both sides using subtraction property of equality. That 4x equals 20. Remember, the goal was to prove that x equals 5. So we will, of course, divide by 4 on both sides to get 5. And so those are our first two proofs. As we close up this video, one of the last things we want to touch about is what a theorem is all about. We've talked about a postulate. Remember, a postulate was just simply a statement that we accepted. It didn't need to be proven. Well, now a theorem is a statement that can be proven. And once the statement is proven, you can use the theorem as a reason in other proofs. So what we mean is once you have proven it, kind of in our context, it's once we've gotten past it, we can use it, okay? Now, we're not going to have time or be able to prove every single theorem in geometry. We could, but there's just physically not enough time to. We're going to prove a lot of them as we continue to go on. A theorem is a statement that can be proven, and there's going to be a multitude of theorems coming our way in this course.